Welcome. Wherever you are listening from, take a moment to slow your breathing, to let the world outside soften just a little. This is not a debate, it is not an argument, and it is not a declaration of certainty. This is a quiet exploration of one of the most powerful ideas humanity has ever created, the idea that the universe had a beginning and that we know how it happened. For nearly a century, the Big Bang Theory has stood as the backbone of modern cosmology. It is the story told in classrooms, documentaries, textbooks, and planetariums across the world. It explains why galaxies are moving away from one another. It explains the faint glow left behind from the early universe. It explains, at least in broad strokes, how everything we see today emerged from something unimaginably small and hot. And because it explains so much, it has become something more than a theory. It has become a foundation, a starting point, a background assumption so deeply embedded in science and culture that questioning it can feel almost taboo. But science does not advance by protecting its foundations. It advances by testing them. The Big Bang Theory was never meant to be a story of absolute truth. It was built as a model, a mathematical framework designed to match observation, and for a long time, it did so remarkably well. When scientists discovered that distant galaxies were moving away from us, the Big Bang offered a coherent explanation. When a faint, uniform radiation was detected across the sky, the theory absorbed it seamlessly. Each success strengthened confidence, and confidence slowly hardened into consensus. Yet beneath this confidence, unease has always existed. The Big Bang Theory does not actually describe the beginning of the universe. It describes what happened after the beginning. It tells us how space expanded, how matter cooled, how structures formed. But when asked what caused the Big Bang itself, what existed before it, or whether before even makes sense, the theory falls silent. Not because the answers are forbidden, but because the mathematics no longer works. At its core, the Big Bang Theory predicts a singularity, a point of infinite density, infinite temperature, and zero volume. At this point, the equations that describe gravity and spacetime break down completely. Time itself loses meaning. Physics, as we know it, stops functioning. This is not a minor detail. It is a warning sign. In science, a singularity does not represent understanding. It represents the edge of it. When equations produce infinities, physicists do not celebrate. They become suspicious. Infinities usually signal that a model has been pushed beyond its domain of validity. They suggest missing physics, incomplete assumptions, or deeper structures yet to be discovered. And yet, the Big Bang Theory places such a singularity at the very foundation of reality. This contradiction has been tolerated for decades, not because it is satisfying, but because there has been no universally accepted alternative. The Big Bang works extraordinarily well for explaining the universe after its first fractions of a second. It predicts expansion, structure, and radiation with stunning accuracy. And so, the discomfort at its beginning has been quietly set aside. But discomfort accumulates. As measurements become more precise, cracks begin to show. Different methods of measuring the universe's expansion produce conflicting results. The early universe appears unexpectedly uniform in ways the theory struggles to explain. Entire components, dark matter and dark energy, are introduced not because we understand them, but because without them, the equations fail. This is where the question begins to shift. The question is no longer, did the Big Bang happen? The question becomes, is the Big Bang the whole story? Science often progresses by asking questions that sound heretical at first. Is Earth really at the center of the universe? Are space and time absolute? Can light behave like both a wave and a particle? Each of these questions challenge deeply held beliefs, not because scientists wanted to reject truth, but because they wanted to refine it. Questioning the Big Bang follows this same tradition. To ask whether the Big Bang Theory is wrong is not to deny evidence. It is to examine interpretation. It is to recognize that a model can be successful and still incomplete, useful and still provisional, powerful and still limited. The universe is under no obligation to conform to the stories we tell about it. The Big Bang Theory may describe a phase transition rather than an absolute beginning. It may represent a rebound from a previous state. It may be one event in a much larger, older cosmic process. Or it may be a local phenomenon mistaken for a universal one. These ideas are not fringe. They are explored seriously in modern theoretical physics, not as replacements yet, but as possibilities. The danger is not in questioning the Big Bang. The danger is in assuming that because a theory works, it must be final. Science is not built on certainty. It is built on approximation. Every major theory in history was eventually revised, expanded, or replaced, not because it was foolish, but because it was incomplete. Newton's gravity was not wrong, but it was not the full story. Classical mechanics still works beautifully, until it doesn't. The same may be true of the Big Bang. The universe we observe today is vast, complex, and ancient beyond comprehension. To assume that its entire origin can be compressed into a single moment of creation, fully described by equations that break at that moment, may say more about our current limits than about cosmic reality. This documentary is not about tearing down science. It is about following it where it leads, even when that direction is uncomfortable. What the Big Bang Theory actually claims. Before asking whether the Big Bang Theory is wrong, it is worth pausing to ask a quieter, more careful question. What does the theory actually claim? Not what it is often said to claim, not what popular images suggest, but what the theory itself truly describes. Because much of the confusion surrounding the Big Bang arises not from disagreement with evidence, but from misunderstanding what the evidence is meant to support. Despite its name, the Big Bang Theory does not describe an explosion. There was no point in space where matter burst outward into emptiness. There was no center. There was no expanding fireball pushing debris into a pre-existing void. These images persist because they are intuitive, because they borrow from familiar experiences. But the universe is not required to be intuitive. What the Big Bang Theory actually describes is expansion specifically, the expansion of space itself. According to the theory, the universe was once in a state that was far hotter, denser, and more compact than it is today. Over time, space expanded, and as it expanded, matter and radiation cooled, allowing structures to form. Galaxies did not fly away from a central blast. Rather, the distance between galaxies increased because the space between them stretched. This distinction matters deeply because it reframes the theory from a story of violent origin to a story of evolution. The Big Bang is not a moment you can point to in space. It is a condition you extrapolate backward in time. When astronomers observe that distant galaxies are moving away from us, they are not seeing motion through space, but motion with space. The fabric itself is changing. The theory rests on three core observations. The first is cosmic expansion. When light from distant galaxies is analyzed, it is stretched toward the red end of the spectrum, indicating that those galaxies are receding. The farther away a galaxy is, the faster it appears to move away. This relationship suggests that the universe is expanding uniformly, not from a single point, but everywhere at once. The second observation is the cosmic microwave background radiation, a faint, nearly uniform glow detectable in every direction. This radiation is interpreted as the cooled remnant of a time when the universe was so hot that atoms could not exist. Light and matter were tightly coupled. As the universe expanded and cooled, light was freed to travel through space. That light, stretched by expansion, is still detectable today as a low-temperature background. The third observation is the relative abundance of light elements, such as hydrogen and helium. According to the theory, the early universe provided conditions under which these elements could form in predictable ratios. Observations broadly match these predictions, lending further support to the model. Taken together, these lines of evidence paint a consistent picture of an expanding universe that was once hotter and denser. This is the domain in which the Big Bang theory is strongest. From fractions of a second after the early expansion onward, it provides a framework that aligns remarkably well with what we observe. But notice something important. None of this evidence directly describes a beginning. The theory does not tell us what caused the expansion. It does not tell us whether the universe came into existence at a particular moment, or whether it transitioned from a prior state. It does not tell us whether time itself began, or whether time existed before the expansion we observe. These questions sit outside the theory's proven domain. Yet in popular understanding, these distinctions often collapse. The phrase, "the universe began with the Big Bang," is repeated so often that it becomes assumed. But within the mathematics, what actually happens is more subtle. When equations describing expansion are extrapolated backward, they eventually reach a point where density and temperature diverge toward infinity. This point is called a singularity. The singularity is often treated as the beginning of everything, but mathematically, it is not a physical event. It is a signal that the equations are being used beyond where they apply. General relativity, the theory that underlies the Big Bang model, works extremely well at large scales, but it is known to be incomplete. It does not incorporate quantum effects, which dominate at extremely small scales and high energies. As the universe is traced backward toward extreme conditions, quantum effects cannot be ignored, and yet the Big Bang model is built using equations that do ignore them. The singularity, then, is not a confirmed moment of creation. It is a placeholder, a boundary beyond which the theory cannot speak. This is a crucial point that often goes unacknowledged. The Big Bang theory does not say that something came from nothing. It does not claim to explain why there is a universe at all. It explains how the universe evolved from a very early state onward. The leap from very early state to absolute beginning is philosophical, not scientific. Over time, however, this leap has become normalized. Educational diagrams show timelines starting at zero. Narratives compress complex mathematics into a simple origin story. The name itself, Big Bang, encourages misunderstanding, and slowly, the public image of the theory drifts away from its actual content. This drift creates tension. When critics challenge the Big Bang, they are often responding not to the theory itself, but to its simplified portrayal. They object to the idea of something emerging from nothing, or to time suddenly beginning, or to an unexplained cause. But these are not claims the theory is equipped to defend. They are interpretations layered on top of it. Within the scientific community, this distinction is well understood, yet not always emphasized. The Big Bang remains the standard model not because it explains everything, but because it explains more than any competing framework so far. It provides a consistent account of expansion, background radiation, and early nucleosynthesis. Where it fails, it is often openly acknowledged. And yet, even within its domain, the theory relies on assumptions that are not directly testable. It assumes homogeneity, that the universe is roughly the same everywhere at large scales. It assumes isotropy, that it looks the same in all directions. These assumptions are supported by observation to a degree, but they are still assumptions. If they fail at scales beyond what we can observe, our conclusions may change. The theory also depends heavily on extrapolation. We observe the universe as it is now, and we use mathematical laws to project backward. This is reasonable, but it is not infallible. Laws derived under one set of conditions may not hold under entirely different ones. The farther back we extrapolate, the more speculative the picture becomes. This brings us to a subtle but important shift. The Big Bang Theory began as an explanation of expansion. Over time, it has been elevated to an explanation of origin. This shift was not driven by new evidence, but by narrative convenience. Humans prefer beginnings. They prefer stories with clear starts. A universe with no origin feels unsettling, incomplete, unresolved. But science is not obligated to satisfy narrative instincts. To say that the Big Bang Theory is wrong may be misleading. To say that it is incomplete is more accurate. It is a powerful description of the universe's early evolution, not a final answer to existence itself. The danger lies in mistaking a successful model for a finished one. The moment physics breaks. There is a point in every scientific theory where confidence gives way to silence, not because the universe becomes unknowable, but because the tools we are using are no longer sufficient. For the Big Bang Theory, that point arrives when we trace the universe far enough back in time that the mathematics itself begins to fail. This failure is not subtle, it is total. As the equations of cosmic expansion are reversed, density increases, temperature rises, space shrinks, the universe becomes hotter, smaller, and more extreme with every step backward. For a long stretch of this journey, physics holds together. The equations remain stable, predictions remain meaningful, but eventually, a boundary is reached where values surge toward infinity. Density becomes infinite, temperature becomes infinite, curvature of space-time becomes infinite. At this point, the equations stop describing reality in any meaningful way. This point is known as a singularity. In everyday language, a singularity sounds like a physical object, a thing that exists at a specific place and time. In mathematics and physics, it is something very different. A singularity is not a confirmed feature of the universe. It is a sign that a model has been pushed beyond its limits. It marks the edge of applicability, not the edge of existence. Physicists are trained to distrust infinities. When equations produce infinite results, it usually means something essential has been left out. In classical mechanics, infinities often signal missing constraints. In electromagnetism, they signal the need for new frameworks. In gravity, they signal the absence of quantum effects. The singularity at the heart of the Big Bang is not an answer. It is a confession of ignorance. Yet this confession has been quietly reframed as a beginning. The Big Bang singularity is often described as the moment when space and time themselves came into existence. But this interpretation goes far beyond what the mathematics can justify. General relativity, the theory used to model the Big Bang, does not include quantum mechanics. It treats space-time as smooth and continuous. At extremely small scales, however, space-time is expected to behave very differently. Quantum fluctuations become dominant. The smooth fabric assumed by relativity may dissolve into something granular, probabilistic, or fundamentally discrete. When we apply general relativity to these extreme conditions, we are using the wrong tool for the job. This mismatch is not a minor technical detail. It is the central reason why the singularity cannot be taken at face value. We are extrapolating a theory known to be incomplete into a regime where its missing pieces matter most. The resulting infinities are not discoveries, they are warnings. To understand why this matters, imagine using a map of city streets to navigate the interior of an atom. The map may be accurate within its intended scale, but it becomes meaningless when applied elsewhere. The problem is not that the map is wrong, it is that the context has changed. The same is true of cosmological equations near the supposed beginning of time. Despite this, the singularity has taken on a powerful cultural role. It provides a clean starting point. It aligns neatly with the idea of creation. It offers a moment of origin that can be placed at the beginning of a timeline. This simplicity is appealing, but simplicity is not evidence. Within physics, the singularity is widely regarded as a placeholder. It marks where new physics is required. It tells us that our current understanding of space, time, and matter is insufficient to describe the earliest moments of the universe. It does not tell us what actually happened there. This distinction is crucial because it opens the door to alternatives. If the singularity is not real, if it is an artifact of incomplete mathematics, then the universe may not have begun in the way the Big Bang narrative suggests. There may have been a prior state. There may have been a transition rather than a creation. Time itself may extend beyond the point where our equations fail. Several modern theories attempt to address this gap. Some propose that quantum effects smooth out the singularity, replacing it with a finite, extremely dense state. Others suggest that the universe underwent a bounce, contracting before expanding again. Still others propose that what we call the Big Bang is merely a phase change within a much older, more complex cosmic history. None of these ideas are yet confirmed, but their very existence underscores an important point. The singularity is not an established fact. It is a signpost pointing toward missing understanding. The breakdown of physics at the singularity also highlights a deeper issue. The Big Bang theory relies on two pillars of modern science, general relativity and quantum mechanics, that do not agree with each other. Relativity governs the large-scale structure of space-time. Quantum mechanics governs the behavior of matter and energy at the smallest scales. Each theory is extraordinarily successful within its domain. Together, they are incompatible. At ordinary conditions, this incompatibility does not matter. The effects are too small to notice. Near the supposed beginning of the universe, it matters completely. Any accurate description of that era must reconcile gravity with quantum effects. Without such a reconciliation, our picture of the beginning remains provisional at best. This is why many physicists are cautious when speaking about the origin of the universe. They recognize that our most trusted equations cannot be applied all the way back. They understand that the moment where physics breaks is not a final answer, but a boundary of current knowledge. And yet, outside of technical circles, this caution is often lost. The singularity is presented as a known event rather than an unresolved problem. The breakdown of mathematics is interpreted as a dramatic origin rather than a limitation. The uncertainty is transformed into certainty through repetition. This transformation has consequences. It shapes how we think about time, causality, and existence itself. If the universe truly began at a singularity, then questions about before may be meaningless. If the singularity is instead a mathematical artifact, then those questions remain open. The difference between these interpretations is not trivial. It determines whether the universe has a finite beginning or an extended past. It influences how we search for deeper laws. It affects whether cosmology aims to explain creation or transition. The moment physics breaks is not a failure of science. It is an invitation. It invites us to look beyond familiar equations, to question assumptions that once seemed solid, to accept that the universe may be stranger, older, and more complex than our current models suggest, and to recognize that the most honest answer to the question of origins may not yet exist. The problem of the singularity. If the singularity were merely an abstract mathematical inconvenience, it could be ignored, but it is not. The singularity sits at the very foundation of the Big Bang narrative, and that placement turns a technical limitation into a conceptual problem. It forces us to confront a difficult question. Can a theory that breaks at its most important moment truly be considered complete? In physics, singularities are treated with suspicion for good reason. They are places where quantities become infinite and infinities rarely describe physical reality. Nature, as far as we can tell, does not contain infinite temperatures, infinite densities, or infinitely small points with unlimited energy. When infinities appear in equations, they usually signal that the equations are being pushed beyond their valid range. This has happened before. In the early days of classical physics, calculations of atomic structure led to infinities that made no sense. Electrons should have spiraled endlessly into nuclei, radiating infinite energy. The problem was not the atom, it was the theory. Quantum mechanics resolved this by introducing new rules that eliminated the infinities entirely. The singularities vanished once the deeper structure was understood. Many physicists suspect the same is true of the Big Bang singularity. The problem is not just that the singularity is mathematically undefined, it is that it erases causality. At the singularity, time itself is said to begin. If time begins there, then there is no before. Without a before, causation loses meaning. Causes precede effects in time. If time does not exist, causation cannot exist either. This makes the singularity not just a physical boundary, but a philosophical one. Some accept this as a feature rather than a flaw. They argue that the universe simply began and that asking what caused it is meaningless. But this stance is not derived from observation. It is derived from resignation. It treats the limits of current theory as limits of reality itself. Others are less comfortable with this conclusion. They point out that physics has repeatedly mistaken boundaries of knowledge for boundaries of existence. The edge of the observable universe was once thought to be the edge of the universe itself. The inability to see beyond a horizon was mistaken for a physical limit. Later, it became clear that horizons reflect observational constraints, not cosmic endings. The singularity may be a similar illusion. Another issue lies in symmetry. The laws of physics, as we know them, are remarkably consistent across time and space. They do not suddenly switch off. Yet the singularity demands exactly that, a moment where the laws cease to apply. This abrupt breakdown is deeply unsettling to physicists, because it violates the expectation that deeper laws should unify, not fragment. If the laws of physics cannot describe the beginning of the universe, then either the laws are incomplete or the beginning is being misunderstood. This leads to an important realization. The Big Bang singularity is not predicted by observation. It is predicted by extrapolation. We do not observe infinite density. We calculate it by extending equations backward beyond where they are known to work. The singularity is not measured. It is inferred, and inference based on extrapolation is always tentative. There is also the issue of scale. General relativity treats spacetime as continuous. Quantum mechanics suggests that at very small scales, reality is granular and probabilistic. The singularity assumes continuity all the way down to zero size. This assumption is almost certainly wrong. At some point, space-time itself should become quantized, preventing true infinities from forming. If space-time has a smallest meaningful unit, then the singularity cannot exist as described. Density would be finite, temperature would be finite. Time would not simply stop. The beginning would become something else, perhaps a transition, perhaps a compression, perhaps a phase change. Several approaches to quantum gravity attempt to address this. Some replace the singularity with a bounce, where contraction turns into expansion. Others smooth it into a dense but finite state, governed by quantum rules. In these models, the Big Bang is not the birth of everything, but a boundary between phases. The universe, in this view, does not emerge from nothing. It transforms. This transformation perspective removes many of the conceptual problems associated with the singularity. Causality is preserved. Time may extend beyond the transition. Physical laws remain applicable, though modified. The universe becomes a process rather than an event. Critically, These models are not speculative fantasies. They are developed by physicists working at the intersection of relativity and quantum theory. They are constrained by mathematics and informed by observation. They exist because the singularity is widely regarded as unacceptable, not because scientists are dissatisfied with the Big Bang's success, but because they are dissatisfied with its incompleteness. The persistence of the singularity in popular narratives reflects inertia more than certainty. It is easier to teach a universe with a beginning than one with an unknown past. It is easier to draw a timeline with a starting point than one that fades into deeper structure. Simplicity wins, even when it misleads. The problem of the singularity, then, is not that it challenges belief. It is that it challenges coherence. A theory that explains expansion, structure, and radiation beautifully, but collapses when asked about its own starting point, is not wrong, but it is unfinished. And unfinished theories are not destinations, they are invitations. The patch that raises more questions. When a theory explains much, but not everything, scientists often respond in a familiar way. They add a new idea, not to replace the theory, but to stabilize it. In cosmology, that stabilizing idea is called inflation. It is one of the most influential and most controversial additions to the Big Bang framework. And like many patches that solve urgent problems, it leaves behind deeper questions that refuse to disappear. Inflation was proposed to address several puzzling features of the universe that the original Big Bang model could not easily explain. Chief among these was uniformity. When we look at the universe on the largest scales, it appears remarkably smooth. The temperature of the cosmic microwave background is almost the same in every direction. Regions of space that are so far apart they should never have been able to exchange information nonetheless look strikingly similar. This is known as the horizon problem. According to standard Big Bang expansion, distant regions of the universe should have evolved independently. There should be noticeable differences in temperature and structure. Instead, there is astonishing consistency. Inflation offers a solution by proposing that the universe underwent a brief but extreme period of expansion very early in its history, expanding faster than light could travel. In this scenario, regions that now appear distant were once close enough to equilibrate before being rapidly pulled apart. Inflation also addresses the flatness problem. The geometry of the universe appears finely balanced, neither strongly curved nor obviously warped. Without inflation, this balance would require extraordinarily precise initial conditions. Inflation smooths out curvature, making the observed geometry more likely. On the surface, inflation looks like a triumph. It resolves multiple issues at once. It fits comfortably into existing mathematics, and it makes testable predictions, some of which appear to align with observation. As a result, inflation has become a standard component of cosmological models. But inflation introduces a new layer of complexity, and with it, new uncertainty. To trigger inflation, physicists must introduce a hypothetical field with unusual properties. This field must have a specific form of energy that drives rapid expansion, then decays in just the right way to allow the universe we observe to form. The nature of this field is unknown. It has never been directly observed. Its properties are inferred rather than measured. This is not necessarily a problem. Many theoretical entities begin this way. The issue arises when the freedom to define this field becomes too broad. There are countless possible inflationary models, each with different assumptions and consequences. Some lead to universes like ours, others do not. Without a clear way to select among them, inflation risks becoming less a prediction and more a framework flexible enough to accommodate almost any outcome. This flexibility worries some physicists. A theory that can explain anything may, in practice, explain nothing. Inflation also shifts the problem of beginnings rather than eliminating it. While it smooths conditions after a certain point, it does not explain why inflation started. It does not explain why the field had the right properties. It does not explain why inflation ended. These questions are pushed further back, closer to the singularity or to whatever replaces it. In some versions of inflation, the process never fully stops. Instead, it continues eternally in different regions of space, creating a vast collection of expanding universes. Our observable universe becomes one bubble among many, each with its own physical properties. This idea, known as eternal inflation, radically alters the meaning of explanation. In an eternally inflating universe, almost anything that can happen will happen somewhere. The laws we observe are no longer uniquely determined by deep principles. They are environmental accidents of where we find ourselves. This raises a troubling question. If our universe is just one of many, chosen by chance, what does it mean to explain its origin at all? Inflation's success in solving early universe puzzles comes at the cost of introducing these philosophical challenges. Some scientists embrace this, arguing that cosmology must confront selection effects and multiverse scenarios. Others see it as a warning sign that the theory is drifting away from empirical grounding and toward speculation. There is also the issue of testability. While inflation makes certain broad predictions, such as the existence of primordial fluctuations, many specific versions of inflation predict different details. Observations can rule out some models, but rarely all. As measurements improve, inflation adapts. New models emerge to fit new data. This adaptability is both a strength and a weakness. Critics argue that inflation has become a placeholder for ignorance. Much like dark energy or dark matter, it fills gaps without revealing underlying mechanisms. Supporters counter that it is the best framework we have, and that future discoveries may clarify its foundations. Both positions coexist uneasily. What is clear is that inflation is not a simple extension of the Big Bang. It is a profound modification that changes how we think about beginnings, causality, and explanation. It transforms the Big Bang from a singular event into part of a longer, more complex story, one that may not have a clear starting point at all. This returns us to the original question. If the Big Bang requires inflation to explain its own consistency, and inflation requires assumptions we cannot yet test, how secure is the foundation we are building on? Is inflation a glimpse of deeper truth, or a temporary scaffold supporting an incomplete structure? Science often advances by building scaffolds. They are not meant to be permanent. They allow work to continue while deeper foundations are sought. Inflation may be such a scaffold, useful, elegant, and provisional. What we really see when we look back in time. When astronomers say they are looking back in time, the statement is both poetic and precise. Light travels at a finite speed. Every photon that reaches a telescope carries with it a history, the conditions of the moment and place where it was emitted. To observe distant galaxies is to observe the universe as it once was, not as it is now. The farther we look, the deeper into the past we see. This simple fact underlies much of modern cosmology. It is how the Big Bang theory is tested. It is how models of cosmic evolution are refined. And it is how the early universe is reconstructed, not by direct observation of a beginning, but by assembling fragments of ancient light into a coherent picture. But this process has limits. No matter how powerful a telescope becomes, it cannot see arbitrarily far back. There is a boundary beyond which the universe is opaque. Before a certain time, the universe was filled with charged particles that scattered light relentlessly. Photons could not travel freely. The universe was a glowing fog, bright but impenetrable. We cannot see past this fog using light, because no light from earlier times can reach us. This boundary is known as the surface of last scattering. It corresponds to the moment when the universe cooled enough for atoms to form, allowing light to travel unimpeded. The radiation released at that time has been stretched by cosmic expansion into the faint microwave glow we observe today. This glow is often described as an image of the infant universe, but it is important to understand what kind of image it is and what it is not. The cosmic microwave background does not show the moment of creation. It does not show the universe at its beginning. It shows the universe hundreds of thousands of years after the processes described by the Big Bang model began. By that time, the most extreme conditions had already passed. The universe had expanded, cooled, and settled into a relatively stable state. Everything before this point, including inflation, the supposed singularity, and the earliest fractions of a second, lies beyond direct observation. This means that much of what we say about the beginning of the universe is inferred rather than seen. We take what we observe at later times and extrapolate backward using mathematical models. This is not unreasonable. It is how much of science works, but extrapolation always carries uncertainty, especially when applied across regimes where physical laws may change. As we push models closer to the earliest times, the assumptions underlying them become increasingly important. We assume that the laws of physics observed today applied in the same form under vastly different conditions. We assume that quantities such as energy and entropy behaved predictably. We assume that space-time itself remained a meaningful concept. These assumptions may be approximately true. They may also fail in subtle ways. Observational cosmology is remarkably precise, but precision does not equal completeness. Measurements of cosmic background radiation reveal tiny fluctuations, minute variations in temperature and density that later gave rise to galaxies and clusters. These fluctuations are often cited as evidence for inflation and early universe physics, and indeed, they are consistent with many inflationary models. But consistency is not confirmation. Different theoretical frameworks can produce similar observational signatures. A smooth background with small fluctuations does not uniquely identify a single origin story. It constrains possibilities, but it does not select one definitively. This is a crucial distinction that is often blurred outside technical discussions. There are also anomalies features in the data that do not fit neatly into the standard picture. Slight asymmetries, unexpected alignments, variations that appear larger than predicted. These features are often dismissed as statistical flukes or artifacts of measurement. Sometimes they are, sometimes they persist across datasets and instruments, lingering without clear explanation. Anomalies are uncomfortable. They sit at the edge of significance, neither decisive nor ignorable. Over time, some fade as data improves. Others remain quietly challenging assumptions. In cosmology, where direct experimentation is impossible, such anomalies carry disproportionate weight. They may be clues, or they may be noise. Distinguishing between the two is one of the field's greatest challenges. Beyond the cosmic microwave background, astronomers look to the large-scale structure of the universe. The distribution of galaxies, filaments, and voids reveals how matter clustered over billions of years. These structures encode information about the early universe, but again, the signal is indirect. It reflects the cumulative effect of gravity, expansion, and unknown components like dark matter. Each layer of inference adds uncertainty. As observations extend deeper, the universe becomes younger, simpler, and harder to interpret. Galaxies appear less evolved. Structures are less defined. The processes governing them are less familiar. At some point, the universe transitions from a place where astrophysics applies to a place where only fundamental physics matters. We have never observed that transition directly. This raises an important question. How confident can we be about events that lie entirely beyond observational reach. Science thrives on testability. The further a claim lies from what can be tested, the more provisional it becomes. Early universe cosmology sits at the edge of this boundary. This does not mean it is unscientific. It means it operates under different constraints. Models are evaluated not by direct verification, but by coherence, consistency, and explanatory power. They must fit known data without introducing contradictions elsewhere. This is a high bar, but it is not the same as experimental confirmation. There is also a tendency to mistake resolution for clarity. As telescopes become more powerful, images become sharper, maps become more detailed, and measurements become more precise. This progress is real and valuable, but it does not extend indefinitely backward. There is a fundamental observational horizon that no amount of engineering can cross using light. Future observations may use other messengers, gravitational waves, neutrinos, or unknown signals to probe earlier times. These avenues hold promise, but they also face immense technical challenges. Even if successful, they will likely reveal new layers of complexity rather than a simple origin story. The idea that we can one day see the beginning of the universe may itself be a misconception. Beginnings, if they exist, may not leave observable traces. They may be transitions rather than events. They may be encoded in structures too subtle to isolate cleanly. What we really see, when we look back in time, is not a starting line, but a fading trail. The closer we get to the earliest moments, the more the trail blurs. The universe does not reveal its origins willingly. It offers hints, patterns, and constraints, but not a clear narrative. This realization tempers certainty. It encourages humility. It reminds us that cosmology, for all its sophistication, is still an interpretive science. It constructs stories from signals, models from measurements, and meaning from mathematics. These stories are powerful, but they are not final. The cosmic microwave background isn't perfect. Few discoveries in science have carried the weight of expectation quite like the cosmic microwave background. When it was first detected, it seemed to confirm a long-standing prediction. If the universe had once been hot and dense, there should be a faint afterglow radiation stretched thin by billions of years of expansion. The discovery of that glow was celebrated as decisive evidence. For many, it settled the debate. But evidence, even powerful evidence, is rarely simple. The cosmic microwave background, often abbreviated as the CMB, is astonishingly uniform. Its temperature varies by only tiny fractions of a degree across the entire sky. This uniformity is one of the strongest pillars supporting the Big Bang framework. It suggests that the early universe was in thermal equilibrium, that energy was distributed evenly before expansion carried regions apart. Yet when scientists began to study the CMB in greater detail, they noticed something unexpected. Beneath the overall smoothness lay subtle irregularities, patterns, and anomalies that did not fit neatly into the simplest models. These irregularities are small, but they matter. Tiny fluctuations in temperature correspond to differences in density in the early universe. These differences eventually grew into galaxies, clusters, and vast cosmic structures. Without them, the universe would be a featureless haze. Their existence is essential, but their precise arrangement raises questions. Some of these anomalies appear aligned in ways that should not happen by chance. Certain large-scale patterns seem to point in particular directions. Others suggest asymmetries between different hemispheres of the sky. These features are often described cautiously, with terms like statistical oddities or cosmic variance. And indeed, they may be coincidences. But their persistence across multiple measurements has kept them from being easily dismissed. One of the most discussed features is the so-called axis, suggested by large-scale temperature variations. If real, It implies a preferred direction in the universe, something that challenges the assumption of isotropy, the idea that the universe looks the same in every direction at large scales. Isotropy is a cornerstone of cosmology. If it fails, even subtly, the implications are profound. Another anomaly involves temperature differences between hemispheres. One side of the sky appears slightly warmer or more variable than the other. The difference is small, but cosmology often hinges on small differences. If the early universe were truly uniform, such asymmetry would be unexpected. There are also regions of unusually low temperature cold spots that stand out against the otherwise smooth background. These features may have explanations within standard physics, but they also invite alternative interpretations. Are they statistical flukes, artifacts of measurement, or hints of processes beyond the standard model? The difficulty lies in interpretation. The CMB is a single realization of a cosmic process. We do not have multiple universes to compare. Statistical analysis must work with one dataset, however precise. This limits confidence. Patterns that appear meaningful may be chance alignments. Patterns that are dismissed may be significant. The line between signal and noise is thin. Inflation is often invoked to explain the overall smoothness and the presence of small fluctuations. Many inflationary models predict a nearly uniform background with random variations. But this flexibility is part of the problem. If a theory can accommodate almost any pattern, then anomalies become less informative. They no longer test the theory, they are absorbed by it. This adaptability has led some physicists to worry that the Big Bang model, combined with inflation, has become too accommodating. Instead of making sharp predictions that can be falsified, it provides a broad framework within which many outcomes are acceptable. This does not make it wrong, but it does weaken its explanatory precision. There is also the issue of foreground contamination. The universe between us and the CMB is not empty. Dust, gas, and radiation from our own galaxy and others can distort measurements. Scientists work diligently to remove these effects, but complete separation is impossible. Residual contamination may influence the patterns we observe. Determining how much of the CMB's structure is primordial and how much is intervening remains an ongoing challenge. Despite these uncertainties, the CMB remains an extraordinary achievement. It offers a snapshot of the universe at a time when it was young and relatively simple. It constrains models in ways no other observation can. But it does not close the case. The CMB does not tell us what happened at the very beginning. It does not reveal the cause of expansion. It does not resolve the singularity. It provides boundary conditions, not origins. Treating it as definitive proof of a specific creation story stretches its meaning beyond what the data can support. This distinction is often lost in popular narratives. The CMB is presented as a photograph of the universe's birth rather than as a measurement of a later stage. The difference matters. A photograph implies direct observation. A measurement implies inference. As measurements improve, some anomalies may fade, others may sharpen. Either outcome is informative. If they fade, the standard model gains confidence. If they persist, the pressure to revise assumptions increases. Science advances either way. The cosmic microwave background is not perfect. It is not uniform in every detail. It is not free from ambiguity. And it is not the final word on cosmic origins. It is a powerful clue, but clues do not tell the whole story. The expansion problem. For much of the 20th century, one idea held steady in cosmology. The universe is expanding, and we know how fast. This expansion rate, known as the Hubble constant, became a cornerstone of the Big Bang framework. Measure it accurately, and you could estimate the age of the universe, test models of cosmic evolution, and refine predictions about its future. For a long time, disagreements over its value were treated as technical issues, expected to fade as measurements improved. They did not fade. Instead, they sharpened. Today, cosmology faces a quiet but persistent crisis. Different methods of measuring the universe's expansion rate produce different answers, and not by small amounts. These discrepancies are large enough that they cannot be easily dismissed as experimental error. They point toward a deeper inconsistency at the heart of the Standard Model. This is known as the Hubble tension. There are two primary ways to measure cosmic expansion. One looks outward and backward, using the early universe as a reference. The other looks nearby and forward, using the present universe as a guide. In principle, both should converge on the same value. In practice, they do not. The first method relies on the cosmic microwave background. By analyzing the tiny fluctuations in this ancient radiation, scientists infer conditions in the early universe and extrapolate forward using the standard cosmological model. This approach yields a relatively low expansion rate. The second method measures distances to nearby galaxies using objects whose intrinsic brightness is known or can be calibrated. By observing how fast these galaxies appear to be moving away, scientists derive a higher expansion rate. The difference between these two values is not subtle, it is persistent, statistically significant, and resistant to easy explanation. At first, the discrepancy was treated cautiously. Measurement techniques were refined. Data was reanalyzed. Instruments were recalibrated. Systematic errors were hunted aggressively. Each improvement tightened uncertainties, but the gap remained. As precision increased, so did confidence that the tension was real. This is deeply unsettling for cosmology. If the standard model of the universe is correct, if the Big Bang, inflation, dark matter, and dark energy together describe cosmic history accurately, then the expansion rate inferred from the early universe should match what we measure today. The fact that they do not suggests that something is missing. One possibility is that there are unknown errors in one or both measurement methods. This remains an active area of investigation. But as techniques mature and independent groups replicate results, the likelihood of simple error diminishes. Another possibility is that new physics is required. This is where the implications become profound. To reconcile the discrepancy, physicists have proposed modifications to the Standard Model. Some suggest that dark energy behaves differently than assumed. Others propose additional particles or fields that influence the early universe but faded later. Still others consider changes to gravity itself. Each proposal comes with consequences. Altering early universe physics affects predictions for the cosmic microwave background. Changing late universe behavior affects galaxy formation and structure. Any solution must thread a narrow needle, fixing the expansion problem without breaking the rest of cosmology. The fact that such solutions are being seriously considered reflects how significant the tension has become. The expansion problem also raises a subtle but important question about extrapolation. Much of cosmology relies on extending known laws across immense spans of time and space. We assume that the same rules applied billions of years ago and continue to apply today. The Hubble tension challenges this assumption. It hints that the universe's behavior may not be as uniform across epochs as we thought. If the expansion rate has changed in unexpected ways, then our reconstruction of the universe's past may need revision. The timeline inferred from early universe models may not align cleanly with the universe we observe now. This misalignment does not invalidate the Big Bang, but it complicates it. There is also a philosophical dimension to this problem. The standard cosmological model is remarkably successful, but it is also remarkably complex. It relies on components, dark matter and dark energy, that have never been directly detected. These components are inferred because they make the equations work. The expansion problem adds another layer of inference. pushing the model further from direct observation. At what point does a model become too flexible? This is not a rhetorical question. In science, explanatory power must be balanced against falsifiability. A theory that can be adjusted endlessly to fit new data risks losing its predictive strength. The expansion problem forces cosmologists to confront this balance explicitly. Some researchers argue that the tension will eventually dissolve as data improves. Others suspect it is a signpost pointing toward a deeper theory, one that encompasses the Big Bang but revises its details. Both positions are plausible. The uncertainty itself is the point. What makes the expansion problem especially significant is that it emerges from the present universe. It does not depend on speculative early universe physics alone. It is grounded in observations of galaxies, stars, and cosmic structures we can study directly. This grounds the crisis in empirical reality. If the universe is expanding faster now than our models predict, then our understanding of cosmic history may be incomplete. The story we tell about the universe's beginning, evolution, and fate may require revision, not abandonment, but refinement. The Big Bang Theory has always been a framework, not a finished script. The expansion problem reminds us that frameworks evolve. They absorb new information, they adapt, or they are replaced. This tension also highlights a broader truth about science. Progress does not always come from new discoveries. Sometimes it comes from contradictions that refuse to go away. When measurements disagree, they force theories to change. The discomfort they create is productive. The expansion problem does not tell us that the Big Bang is wrong, but it tells us that the universe is not done surprising us. It tells us that even our most trusted models are provisional, subject to revision as evidence accumulates. Dark matter and dark energy, placeholders or reality. Modern cosmology rests on an unusual foundation. When scientists describe the contents of the universe, they often begin with a striking admission: almost everything is invisible. Ordinary matter, the atoms that form stars, planets, and living beings, accounts for only a small fraction of the cosmic total. The rest is divided between two entities that cannot be seen directly, cannot be touched, and have never been isolated in a laboratory. They are known as dark matter and dark energy. Together, these unseen components dominate the universe. Dark matter is invoked to explain why galaxies rotate the way they do. When astronomers measure the speed at which stars orbit the centers of galaxies, they find that visible matter alone cannot account for the motion. Stars are moving too fast. According to known laws of gravity, galaxies should tear themselves apart. They do not. Something unseen must be holding them together. Dark energy is introduced to explain why the expansion of the universe is accelerating. Instead of slowing down under gravity, distant galaxies appear to be moving away faster over time. This behavior contradicts earlier expectations. To account for it, cosmologists propose a form of energy that permeates space itself, pushing it apart. These ideas are not arbitrary. They arise from careful observation and mathematical necessity. Without dark matter, galaxies would not form as they do. Without dark energy, the universe's large-scale expansion would not match measurements. In this sense, both concepts are extraordinarily successful, and yet they remain profoundly mysterious. Dark matter has never been directly detected. Decades of experiments have searched for candidate particles, building ever more sensitive detectors deep underground, in space, and in particle accelerators. So far, none have produced definitive results. The absence of detection does not disprove dark matter, but it does complicate the story. The more invisible something remains, the more questions arise about its nature. Dark energy is even more elusive. It is not associated with particles in any conventional sense. It does not cluster. It does not dilute as the universe expands. Its defining feature is that it behaves like a property of space itself. Some describe it as vacuum energy. Others treat it as a constant of nature. Still others propose it is a sign that gravity behaves differently at cosmic scales. In both cases, these entities function as explanatory tools. They are introduced because they make the equations work. When observations diverge from prediction, dark components are added to restore agreement. This approach is pragmatic, but it invites scrutiny. Are dark matter and dark energy discoveries? Or are they placeholders, names assigned to gaps in understanding? History offers relevant parallels. In the past, discrepancies in planetary motion led astronomers to propose unseen planets. In one case, this worked. Neptune was discovered precisely where calculations predicted. In another case, the discrepancy in Mercury's orbit resisted explanation. No planet was found. Instead, the theory of gravity itself was revised. General relativity replaced Newtonian mechanics, resolving the problem without invoking hidden objects. Dark matter and dark energy may fall into either category. They may represent real components of the universe, awaiting discovery. Or they may signal that our understanding of gravity and space-time is incomplete at large scales. The evidence alone does not yet decide. This uncertainty matters because the Big Bang model depends heavily on these components. The early universe's evolution, the formation of structure, and the expansion history all rely on dark matter and dark energy behaving in specific ways. If their nature changes, the narrative changes with it. There is also a cumulative effect. Each time a new unseen component is added to preserve a theory, confidence shifts subtly. The model becomes more complex, less intuitive, and harder to falsify. This does not make it wrong, but it does raise the bar for future testing. Some physicists are comfortable with this complexity. Nature, they argue, is under no obligation to be simple. Others worry that cosmology is drifting toward a framework that explains observations by layering assumptions rather than uncovering underlying mechanisms. This tension is not about belief, it is about strategy. Should science continue refining the current model, trusting that direct detection or deeper theory will eventually justify its components? Or should it remain open to more radical revisions, changes to gravity, spacetime, or cosmic history that reduce the need for unseen entities? Both paths are being explored. Modified gravity theories attempt to explain galactic dynamics without dark matter. Alternative expansion models attempt to address acceleration without dark energy. None have yet achieved the same broad success as the standard model, but their existence underscores an important point. The current framework is not uniquely determined by evidence. Dark matter and dark energy may be real. They may also be signs that we are interpreting the universe through incomplete lenses. Until they are directly observed or replaced by deeper understanding, their status remains provisional. This provisional status does not undermine cosmology, it defines it. Science advances by naming unknowns, not by pretending they do not exist, but naming unknowns is not the same as explaining them. As long as most of the universe remains invisible, our stories about its origin must remain tentative. The Big Bang theory incorporates dark matter and dark energy because it must, but why gravity doesn't fit? Of all the forces that shape the universe, gravity is the most familiar and the most resistant to understanding. It governs the motion of planets, the formation of galaxies, and the large-scale structure of the cosmos. It is the force that gives weight to matter and shape to space-time itself. And yet, when cosmologists attempt to describe the very beginning of the universe, gravity becomes the greatest obstacle of all. The problem is not that gravity is weak or mysterious in everyday life. It is that gravity, as described by general relativity, does not coexist comfortably with the rules that govern everything else. Quantum mechanics describes particles, fields, and probabilities with extraordinary precision. General relativity describes space-time and gravity as smooth, continuous geometry. Each theory works brilliantly in its own domain. Together, they clash. This clash becomes unavoidable at the earliest moments of the universe. As we trace the Big Bang backward, densities rise and distances shrink. Gravity becomes dominant at scales where quantum effects can no longer be ignored. But general relativity has no built-in mechanism to handle quantum uncertainty. It treats space-time as a classical object, infinitely divisible and perfectly smooth. Quantum mechanics, by contrast, suggests that reality at small scales is discrete, fluctuating, and probabilistic. When gravity is forced into this quantum regime without modification, the mathematics breaks down, predictions diverge, singularities appear, the equations lose meaning. This is not because the universe becomes illogical, but because our description of it does. For decades, physicists have sought a theory of quantum gravity, a framework that unifies gravity with quantum mechanics. Such a theory would describe space-time itself as a quantum object, capable of fluctuation and interaction. It would resolve singularities and provide a consistent description of extreme conditions, including those near the supposed beginning of the universe. Despite enormous effort, no such theory has been experimentally confirmed. Several candidates exist. Some attempt to quantize space-time directly, breaking it into fundamental units. Others introduce additional dimensions or new mathematical structures. Each approach offers insights, but none has yet produced testable predictions that distinguish it decisively from alternatives. Without experimental guidance, theory proliferates. This absence of quantum gravity is not a minor inconvenience. It means that any account of the universe's origin is necessarily incomplete. The Big Bang model relies on general relativity precisely where general relativity is expected to fail. It is like building a bridge that extends confidently from both sides but collapses at the center. Because gravity governs the expansion and curvature of space-time, its behavior at early times determines everything that follows. If gravity behaves differently under extreme conditions, then the timeline, structure, and even existence of a singularity may change. The beginning of the universe may look nothing like current models suggest. This uncertainty extends to inflation. Inflationary models rely on gravity interacting with hypothetical fields under extreme conditions. Without a quantum theory of gravity, these interactions are approximated. The results may be broadly correct or subtly wrong in ways that matter enormously. There is also the issue of energy. In general relativity, energy curves space-time. In quantum mechanics, energy fluctuates even in empty space. These fluctuations become significant at small scales. How they influence gravity is unknown. Vacuum energy, which may be related to dark energy, behaves in ways that defy straightforward calculation. Predictions differ from observation by vast factors. Something is clearly missing. This mismatch is one of the deepest unsolved problems in physics. It suggests that our understanding of gravity is incomplete, not just technically, but conceptually. Gravity may not be a force in the same sense as others. It may emerge from deeper principles. It may reflect statistical behavior of microscopic degrees of freedom we have yet to identify. If gravity is emergent rather than fundamental, then the Big Bang narrative must be reconsidered. Emergent phenomena do not exist at all scales. They arise under certain conditions. The universe's earliest moments may predate gravity as we know it. In such a scenario, talking about a gravitational singularity at the beginning becomes meaningless. This possibility reframes the entire discussion. The Big Bang may not be the start of space-time, but the moment when space-time took on the properties we recognize. Before that, reality may have been governed by different rules that do not map neatly onto our concepts of time and space. The failure to unify gravity with quantum mechanics is not due to lack of effort. It reflects the profound difficulty of reconciling two deeply successful but incompatible descriptions of nature. Until this reconciliation is achieved, cosmology remains provisional at its most fundamental level. This does not diminish its achievements, it contextualizes them. The Big Bang Theory explains much about the universe's evolution, but it cannot fully explain the universe's origin without a theory of gravity that works at all scales. Gravity does not fit neatly into the story as it is currently told. And this misfit is not an embarrassment, it is a clue. It suggests that the beginning of the universe may not be accessible through existing frameworks alone. It suggests that new concepts, not just new equations, are required. And it suggests that the question of whether the Big Bang is wrong may hinge less on data than on the deeper structure of physical law. Quantum mechanics versus the Big Bang. At the smallest scales of reality, the universe behaves in ways that defy everyday intuition. Particles exist in multiple states at once. Outcomes are governed by probability rather than certainty. Observation itself alters what is observed. This strange and counterintuitive framework, quantum mechanics, has been tested more thoroughly than almost any other theory in science. Its predictions have been confirmed with astonishing precision. And yet, when quantum mechanics is brought face to face with the Big Bang, the two do not agree. The Big Bang theory relies on classical descriptions of space-time. It assumes that time flows smoothly, that space can be divided endlessly, and that physical quantities evolve deterministically according to well-defined equations. Quantum mechanics rejects these assumptions. It replaces certainty with uncertainty, continuity with discreteness, and determinism with probability. This conflict becomes unavoidable when we consider the earliest moments of the universe. As we move backward in time toward higher energies and smaller scales, quantum effects become dominant. Particles fluctuate violently. Energy appears and disappears. Fields behave unpredictably. In such an environment, the smooth space-time assumed by general relativity may not exist at all. Time itself may lose its familiar meaning. Quantum mechanics suggests that time may not be fundamental. In some formulations, time emerges from correlations between quantum systems rather than existing as a universal background. If time is emergent, then the idea of a moment when time began becomes deeply problematic. Beginnings require a temporal framework. Without time, there is no before or after only relationships. This challenges one of the most common interpretations of the Big Bang, that it marks the beginning of time itself. If time is emergent, then what we call the Big Bang may represent a transition from a timeless quantum state into a classical space-time regime. In this view, the universe did not spring into existence at a singular moment. Instead, it underwent a change in behavior, a reorganization of degrees of freedom that gave rise to time as we experience it. Several approaches to quantum cosmology explore this idea. In some models, the universe is described by a wave function, a mathematical object that encodes all possible configurations. The evolution of this wave function does not require an external time parameter. Time emerges only when certain conditions are met, such as the formation of large-scale structures. In such models, asking what happened before the Big Bang is like asking what lies north of the North Pole. The question assumes a framework that no longer applies. But unlike geographic analogies, this is not a settled conclusion. It is a possibility among many. Other approaches suggest that quantum fluctuations could give rise to entire universes. In these scenarios, the Big Bang is not a unique event, but a common outcome of underlying quantum processes. Universes may appear spontaneously, governed by probabilities rather than causes in the classical sense. Our universe would then be one realization among many. This idea unsettles traditional notions of explanation. In classical physics, events have causes. In quantum mechanics, events have probabilities. Applying this logic to the universe as a whole forces a re-evaluation of what it means to explain existence. The Big Bang becomes less a cause and more a consequence of deeper statistical laws. There is also the issue of measurement. Quantum mechanics depends on observers and interactions. In the early universe, there were no observers in the conventional sense. How, then, did quantum possibilities resolve into the definite structures we see today? Some interpretations suggest that decoherence, the interaction of quantum systems with their environment, played a role. Others propose that classical behavior emerges naturally as systems grow in complexity. None of these interpretations are universally accepted. They coexist, each offering a different perspective on how quantum rules might apply at cosmic scales. What unites them is the recognition that the classical picture of a smooth, deterministic beginning is inadequate. The Big Bang theory, as traditionally presented, does not incorporate these quantum subtleties. It assumes a classical starting point and evolves forward. Quantum mechanics, by contrast, resists such a starting point. It dissolves boundaries and blurs distinctions. The tension between these frameworks is not cosmetic. It goes to the heart of how reality is described. This tension is not unique to cosmology. It appears wherever gravity and quantum mechanics intersect. Black holes exhibit similar paradoxes. Singularities arise in their cores as well, signaling breakdowns in classical theory. The fact that both cosmic beginnings and black hole interiors produce the same mathematical failures suggests a shared underlying issue. If singularities are artifacts of ignoring quantum effects, then both black holes and the Big Bang require revision. The universe's beginning may resemble a quantum process more than a classical explosion. It may involve superposition, uncertainty, and emergence, rather than singularity and creation. This reframing does not render the Big Bang useless. It reframes its scope. The Big Bang may describe the transition from a quantum-dominated regime to a classical, expanding universe. It may be a boundary condition rather than an origin. In this role, it remains invaluable. But this role is narrower than popular narratives suggest. Quantum mechanics challenges the Big Bang not by disproving it, but by revealing its limits. It shows that our most trusted descriptions cannot be extended indefinitely. It forces humility. It reminds us that the universe is not obligated to fit into human categories of beginning and end. The question, is the Big Bang wrong? Begins to dissolve into a more nuanced inquiry. Wrong for what purpose? Wrong as an absolute origin story, perhaps. Right as a description of early expansion, almost certainly. Science advances not by choosing sides between theories, but by integrating them into deeper frameworks. The conflict between quantum mechanics and the Big Bang is not a failure. It is a signal that a more comprehensive understanding awaits. The horizon problem. Imagine standing on a shoreline at night, looking out across an ocean so vast that light from the far side could never reach you. Now imagine discovering that the temperature of the water beneath your feet is identical to the temperature on the opposite shore, down to an extraordinary level of precision. No currents connect the two. No winds cross the distance. No exchange of heat is possible. And yet, somehow, the conditions match. This is the essence of the horizon problem. When cosmologists map the universe, they find that regions separated by immense distances so far apart that light has not had time to travel between them since the universe began look astonishingly similar. Their temperatures, densities, and physical properties align far more closely than classical physics would predict. According to the standard Big Bang model, these regions should be causally disconnected. They should not know about one another, and yet they appear coordinated. This is not a subtle discrepancy. It is a fundamental one. To understand why, we need to think carefully about horizons. In cosmology, a horizon defines the maximum distance over which information can travel. Because nothing moves faster than light, there is a limit to how far causal influence can extend over a given period of time. In the early universe, this limit was extremely small. Regions separated by more than that distance could not exchange energy, particles, or information. If the universe began in a hot, dense state and expanded at a steady rate, then distant regions should have evolved independently. Their temperatures should vary. Their properties should differ. Uniformity would require coordination, but coordination requires contact. The horizon problem arises because we see uniformity without an obvious mechanism for contact. Inflation was introduced largely to address this issue. By proposing a brief period of extremely rapid expansion early in cosmic history, inflation allows regions that are now widely separated to have once been close enough to interact. Before inflation, the universe was small and connected. During inflation, space expanded so quickly that those connected regions were pulled far apart, preserving their similarity. At first glance, this seems like a clean solution. It restores causal contact without violating known physical limits. It explains why the universe looks smooth at large scales, and it integrates neatly into the broader Big Bang framework. But the solution raises its own questions. Inflation must occur at precisely the right time, last for the right duration, and end in the right way. Too little inflation fails to solve the horizon problem. Too much inflation creates a universe vastly different from the one we observe. The parameters must be finely tuned. This fine-tuning is often justified by invoking underlying fields or mechanisms, but those mechanisms remain speculative. More importantly, inflation shifts the mystery rather than eliminating it. If the universe required special initial conditions to trigger inflation, then the question of uniformity simply moves one step earlier. Why were the pre-inflationary conditions suitable? Why did the inflating field have the right properties? Why did inflation begin when it did, and why did it stop? In attempting to explain uniformity, inflation introduces a deeper layer of unexplained structure. Some physicists accept this as the cost of progress. Others see it as a sign that the horizon problem may point toward a more radical revision of cosmology. Perhaps the universe did not begin in the way the Big Bang model assumes. Perhaps the early universe was not governed by the same concepts of distance and causality that apply today. There are alternative approaches that attempt to address the horizon problem without inflation. Some propose that the speed of light was higher in the early universe, allowing distant regions to communicate more easily. Others suggest that space itself emerged gradually, rather than existing fully formed from the start. In such scenarios, uniformity arises naturally, not because of rapid expansion, but because the universe was never fragmented to begin with. These ideas are controversial, and none have replaced inflation as the dominant framework. But their existence highlights an important point. Inflation is not the only way to resolve the horizon problem. It is the most widely accepted, but not the most definitive. The horizon problem also reveals something deeper about how we think. We tend to assume that current physical laws applied unchanged at all times. We assume that concepts like distance, speed, and causality have always meant what they mean now. But these assumptions may not hold at the deepest levels of reality. In quantum physics, non-local correlations exist, connections that do not depend on distance in the usual way. Entangled particles can exhibit coordinated behavior instantaneously, without exchanging information through space. While this does not allow faster-than-light communication, it does challenge classical intuitions about separation and influence. Some physicists wonder whether similar principles might apply at cosmological scales in the early universe. Perhaps the universe began in a state where space-time itself was not yet fully defined. Perhaps uniformity is a relic of that pre-space-time phase, carried forward as classical space emerged. If this is the case, then the horizon problem is not a problem at all. It is a clue. It suggests that the universe's earliest state may have been fundamentally different from anything we can observe today. It hints that the Big Bang may mark not the creation of everything, but the moment when familiar structures, space, time, and separation came into being. From this perspective, the Big Bang theory describes a transition rather than an origin. It tells us what happened after the universe became classical, not what preceded that emergence. The horizon problem exposes the limits of that description. Uniformity, then, is not evidence of a perfectly tuned explosion. It may be evidence of a deeper, more connected phase of reality, one that our current theories only gesture toward. The horizon problem remains unresolved not because inflation fails entirely, but because it does not close the question. It offers a mechanism, but not a final explanation. It restores consistency, but at the cost of introducing new assumptions that themselves demand explanation. In science, such situations are not failures, they are turning points. The horizon problem has forced cosmology to confront the possibility that the universe's beginning cannot be understood using classical intuition alone. It has pushed the field toward quantum cosmology, toward emergent space-time, toward ideas that challenge the very language we use to describe origins. And in doing so, it brings us back to the central question of this documentary. If the Big Bang theory requires increasingly complex additions to remain coherent, if it relies on assumptions that may not apply at the deepest level, and if it cannot fully explain the uniformity we observe without invoking speculative mechanisms, then in what sense is it complete? Alternative universes, alternative beginnings. When a scientific model begins to strain under its own assumptions, researchers do not abandon it immediately. Instead, they explore the edges. They ask, what happens if a foundational premise is altered, relaxed, or replaced? In cosmology, this process has given rise to a wide landscape of alternative models, visions of the universe that do not begin with a singular explosion, but with something quieter, deeper, and far less final. These alternatives are not reactions against evidence. They are responses to unanswered questions. The Big Bang theory, as we have seen, describes expansion with great success. But its story of origins depends on extrapolations that lead to breakdowns, singularities, fine-tuning, unexplained uniformity. Alternative models ask whether these breakdowns are telling us something essential, that the universe's beginning is being mischaracterized. One class of alternatives proposes that the universe did not begin at all, not in the sense of emerging from nothing. Instead, it suggests that what we call the Big Bang was a transition from a prior state. The universe, in this view, has a deeper history that does not appear in the standard timeline because our equations stop working there. These models vary widely in detail, but they share a common intuition. Beginnings are suspicious. In physics, absolute beginnings are rare. Phase transitions are common. Water does not come into existence when it freezes. It changes form. Matter does not appear when a star ignites. It reorganizes. From this perspective, the Big Bang may represent a cosmic phase change, a restructuring of reality, rather than its creation. Some models envision a universe that existed in a compressed or static state before expanding. In these scenarios, time did not begin at the Big Bang. Instead, it passed through it. The universe may have been contracting, cooling, or evolving in a way that is difficult to describe using familiar concepts. Expansion marks a change in behavior, not a starting point. Other approaches propose that our observable universe is only a region within a much larger structure. The Big Bang, then, is not a global event, but a local one, like the formation of a bubble within a vast, ongoing process. Beyond our observational horizon, other regions may exist with different histories, governed by similar or different physical laws. These ideas challenge intuition, but they arise naturally from attempts to reconcile cosmology with quantum physics. If quantum fluctuations can produce structures at small scales, perhaps similar processes operate at cosmic scales. Universes may form the way particles do, not from nothing, but from instability within a deeper background. In such models, the question, "Why did the universe begin?" transforms into, "Why did this universe take this form?" The focus shifts from creation to selection. This shift has profound implications. It reframes cosmology from a search for a singular origin to an exploration of possible histories. The universe becomes one realization among many, not necessarily in a multiverse sense, but in the sense that multiple outcomes were possible. There are also models that dispense with expansion altogether, at least in its traditional interpretation. In these frameworks, the redshift of galaxies, the key evidence for expansion, is reinterpreted. Instead of space stretching, light itself may lose energy over time, or interactions with unknown fields may alter its wavelength. These ideas are controversial and face significant challenges, but they illustrate the willingness of scientists to question even the most entrenched assumptions. The value of such alternatives is not that they are likely to replace the Big Bang tomorrow, it is that they expose the contingency of our current picture. They remind us that the Big Bang is not the only way to explain the universe we observe. It is the most successful so far, but success does not imply exclusivity. Alternative beginnings also intersect with philosophy in unavoidable ways. If the universe did not begin, then questions of cause and purpose take on new forms. If it emerged from a deeper process, then explanation becomes layered rather than linear. The origin of everything may not be a single answer, but a hierarchy of answers, each valid at a different level. This layered view aligns with how science often progresses. Chemistry emerges from physics, but it is not reducible to it in practice. Biology emerges from chemistry, but it introduces new principles. Consciousness emerges from neural activity, but it resists simple explanation. The universe itself may be similar, emerging from deeper laws that we are only beginning to glimpse. Alternative models also help clarify what is at stake in the Big Bang debate. The question is not whether the universe expanded from a hot, dense state. That much is strongly supported by evidence. The question is whether that state represents the absolute beginning of everything, or merely the earliest phase we can currently describe. This distinction is often lost in public discourse. The Big Bang is portrayed as a definitive answer to existence itself. In reality, it is a boundary of knowledge, a place where explanation becomes tentative. Alternative models exist precisely because scientists take that boundary seriously. Some of these models may ultimately fail, others may converge with future discoveries. Most will be revised or abandoned as new data arrives. This is not a weakness, it is how science explores the unknown. The existence of multiple plausible beginnings suggests that the universe's origin is not yet settled. It suggests that the Big Bang theory, while powerful, is not the final word. It invites patience and openness rather than premature certainty. As we move deeper into these alternatives, one idea appears again and again: continuity. Whether through prior states, larger structures, or emergent processes, many models resist the notion of a sudden creation. They favor stories where reality persists, transforms, and reorganizes. The cyclic universe. There is something deeply human about the idea of cycles. We see them in seasons, in tides, in birth and decay. Long before modern science, cultures imagined the cosmos itself as rhythmic, expanding, contracting, renewing itself over vast spans of time. For much of scientific history, these ideas were set aside in favor of linear narratives with clear beginnings. But as cosmology has matured, the notion of a cyclic universe has returned not as myth, but as a serious scientific possibility. The cyclic universe proposes that the Big Bang was not the beginning of everything, but the latest in a long sequence of cosmic events. According to these models, the universe undergoes repeated phases of expansion and contraction, or transformation, across immense timescales. Each cycle may look different, each may erase traces of the last, but the overall process continues. In its simplest form, a cyclic universe expands from a dense state, slows, reverses, and collapses back into another dense state, which then triggers a new expansion. This picture resembles a cosmic heartbeat, but simplicity is deceptive. Realistic cyclic models are far more subtle. One of the earliest challenges to cyclic cosmology came from thermodynamics. Entropy, the measure of disorder, tends to increase over time. If the universe cycles endlessly, entropy should accumulate with each cycle, making each subsequent universe larger, colder, and more diffuse. Eventually, cycles would become impossible. This argument led many physicists to dismiss cyclic models as unworkable. But modern approaches revisit this conclusion. Some cyclic models propose mechanisms that reset entropy between cycles, effectively clearing the cosmic slate. Others suggest that entropy is redistributed into inaccessible degrees of freedom, such as extra dimensions, allowing each cycle to begin in a low entropy state. These ideas are speculative, but they demonstrate that thermodynamics does not definitively rule out cycles, it constrains them. Another class of cyclic models avoids full contraction altogether. Instead of collapsing to a singular point, the universe reaches a minimum size and undergoes a bounce. Quantum effects are often invoked to prevent true singularities, replacing them with finite, extremely dense states. The bounce marks the transition between contraction and expansion, smoothing out infinities and preserving continuity. In these scenarios, the Big Bang becomes the aftermath of a bounce rather than a creation event. The universe expands because it rebounded, not because it emerged from nothing. This reframing resolves the singularity problem by eliminating it entirely. There is no point of infinite density, only a turning point governed by quantum rules. Cyclic models also offer intriguing solutions to other cosmological puzzles. Uniformity, for example, may arise naturally if the universe has undergone many cycles. Irregularities smooth out over time. Each cycle begins more homogeneous than the last. The horizon problem becomes less mysterious when the universe has had ample time to equilibrate across cycles. Structure formation, too, may be influenced by past cycles. Fluctuations seeded in one cycle could imprint patterns in the next. Some models suggest that information survives bounces in subtle ways, shaping the large-scale structure we observe today. These ideas push the boundaries of testability. Evidence for previous cycles would be extraordinarily difficult to detect. Traces, if they exist, would be faint and ambiguous. This does not render the models unscientific, but it does place them at the edge of empirical inquiry. Critics argue that cyclic models risk becoming unfalsifiable. Proponents counter that the same criticism applies to many inflationary scenarios. The debate highlights a broader tension in cosmology: how to evaluate theories when direct experimentation is impossible. Cyclic universes also carry philosophical weight. They dissolve the question of ultimate beginnings. If the universe has no first cycle, then existence does not require a starting point. The cosmos becomes self-contained, governed by laws that allow endless transformation without external cause. This does not answer every question. It replaces one mystery with another. Why does the cycle exist at all? Why do the laws permit such behavior? These questions persist. But they are framed differently, less as puzzles about creation, more as inquiries into structure. Importantly, cyclic models are not claims that the Big Bang theory is false. They often incorporate Big Bang-like expansion phases within each cycle. The difference lies in interpretation. The Big Bang becomes a chapter, not the opening line. This distinction matters because it changes what cosmology is trying to explain. Instead of asking how everything came from nothing, cyclic models ask how order arises from repetition, how stability emerges from change, and how continuity can coexist with transformation. The cyclic universe remains speculative. It competes with inflationary and multiverse models, each with its own strengths and weaknesses. None has yet achieved decisive empirical support, but their coexistence is telling. It reflects the fact that cosmology has reached a point where foundational assumptions are once again in play. The return of cyclic ideas signals dissatisfaction with singular beginnings. It suggests that many physicists find the concept of a universe emerging, fully formed from a mathematical breakdown, unsatisfying. They seek stories that preserve causality, continuity, and physical law across all regimes. Whether the universe truly cycles remains unknown. What is known is that the Big Bang theory, as commonly understood, does not close the door on such possibilities. It leaves room, intentionally or not, for deeper histories and recurring patterns. The eternal universe hypothesis. Among all the alternatives to a universe with a beginning, none is more unsettling or more elegant than the idea that the universe may be eternal, not cyclic, not repeatedly reborn, but continuous. No first moment, no ultimate starting point, just existence extending indefinitely into the past, shaped by laws that do not require creation to function. For much of modern science, this idea was dismissed almost instinctively. The discovery of cosmic expansion seemed to demand an origin. If the universe is getting larger, then surely it must have once been smaller. And if it was smaller, then tracing that process backward appears to lead inevitably to a beginning. But appearances can be deceptive. An eternal universe does not deny expansion. It denies that expansion must imply creation. It suggests that expansion is a phase, a behavior of the universe under certain conditions, rather than proof of absolute origin. Just as rivers flow without implying the creation of water itself, the universe may change without implying that it began. In eternal models, the Big Bang is reinterpreted not as the birth of the universe, but as the onset of the current expansion phase. Before that phase, the universe may have existed in a different form, perhaps static, perhaps slowly evolving, perhaps governed by rules we do not yet fully understand. Some eternal models propose that the universe existed in a quasi-steady state before expansion began. Others suggest a slow contraction that eventually transitioned into expansion without a singularity. Still others envision a timeless background from which classical spacetime emerged. In each case, the key idea is continuity rather than creation. One of the strongest motivations for an eternal universe comes from discomfort with absolute beginnings. In physics, laws describe relationships and evolution. They do not easily describe emergence from nothing. A universe that exists eternally avoids the question of why something came from nothing by removing nothing from the picture entirely. This does not eliminate mystery. It relocates it. Instead of asking what caused the universe to begin, we ask why the universe has the properties it does, why these laws, why this structure, why this balance. These questions remain profound, but they are different in character. They concern form rather than existence. Eternal universe models also interact intriguingly with quantum mechanics. In some quantum cosmological frameworks, the universe exists as a timeless quantum state. Classical space-time and the sense of time flowing emerges only under certain conditions. In such views, the universe does not begin in time. Time begins within the universe. This inversion challenges deeply held intuitions. We are accustomed to thinking of time as a container in which events occur. Quantum cosmology suggests that time may be a derived concept, a consequence of correlations and change, rather than a fundamental backdrop. If time is emergent, then asking when the universe began may be like asking where a circle begins. The question presupposes a structure that does not apply at the most fundamental level. Eternal models also address some of the fine-tuning problems that trouble Big Bang cosmology. If the universe has existed for an indefinite duration, then it has had ample opportunity to settle into stable configurations. Uniformity and structure may arise not from precise initial conditions, but from long-term evolution. Critics of eternal models often raise thermodynamic objections. Entropy, they argue, increases over time. In an eternal universe, entropy should reach a maximum, resulting in a featureless equilibrium incompatible with the structured universe we observe. This argument is powerful but not decisive. Some eternal models propose mechanisms that allow entropy to increase locally while remaining bounded globally. Others suggest that what we call entropy depends on coarse graining, on how we choose to describe states. In a universe without a beginning, entropy may not have a global maximum in the way classical intuition suggests. These ideas are contentious, and none are universally accepted. But they illustrate that eternity is not ruled out by current physics. It remains a live possibility. There is also a psychological dimension to the resistance against eternal universes. Beginnings provide narrative closure. They offer a moment of origin, a place to anchor explanation. Eternity resists such anchoring. It forces us to accept existence without an initiating event. For some, this feels unsatisfying. For others, it feels more honest. Importantly, the eternal universe hypothesis does not deny the success of the Big Bang theory within its domain. It reframes it. The Big Bang becomes a description of a transition in the universe's behavior, not the origin of existence itself. Expansion is real. Early heat and density are real, but they do not exhaust the story. This reframing aligns with a broader pattern in science. Many phenomena, once thought fundamental, turn out to be emergent. Temperature emerges from molecular motion. Pressure emerges from collisions. Time, perhaps, emerges from change. The universe's beginning may be another such emergent illusion. If the universe is eternal, then the question, is the Big Bang wrong, takes on a new meaning. The theory may be right about expansion and early conditions, but wrong about what those conditions represent in the grand scheme of existence. The idea of an eternal universe is not a conclusion. It is a challenge to our models, to our intuitions, and to our desire for definitive answers. It asks us to consider that reality may not conform to the narrative structures we find most comforting. Why scientists still teach the Big Bang. Given everything we have explored, the singularity problem, inflation's uncertainties, the horizon problem, dark components we cannot see, tensions in expansion measurements, and serious alternatives to a cosmic beginning, it is reasonable to ask a simple question. Why, then, is the Big Bang theory still taught as the standard model of the universe? The answer is not stubbornness, it is not ideology, and it is not deception. The answer lies in how science actually works. Science does not wait for perfect theories. It works with the best available ones. A theory earns its place not by explaining everything, but by explaining more than its competitors while remaining internally consistent and empirically grounded. By that measure, the Big Bang Theory remains extraordinarily successful. At its core, the Big Bang is not a claim about creation. It is a framework for describing cosmic evolution. It explains why the universe is expanding. It explains why distant galaxies exhibit redshift. It explains why the universe was once hotter and denser than it is today. It predicts the existence and basic properties of the cosmic microwave background. It accounts for the relative abundance of light elements. These are not philosophical achievements. They are observational ones. No alternative model currently matches this breadth of explanatory power with comparable simplicity. This is a crucial point. Science favors models that do more with less. The Big Bang Theory, despite its unresolved edges, provides a coherent narrative linking a wide range of phenomena. It is not complete, but it is productive. It allows scientists to make predictions, design experiments, and interpret data within a shared framework. In education, this practicality matters. Students need a working model before they can appreciate its limitations. Teaching the Big Bang does not mean teaching certainty. It means teaching a foundation upon which questions can be built. There is also an important distinction between a theory being wrong and being incomplete. In everyday language, these ideas blur together. In science, they are very different. Newtonian gravity was not wrong in the domains where it applied. It was incomplete. It failed at extreme speeds and strong gravitational fields. Yet it is still taught, used, and relied upon because it works exceptionally well in most situations. The Big Bang occupies a similar position. Within the regime of observable cosmic history from fractions of a second after the early expansion onward, it works remarkably well. Its equations describe the universe's behavior with precision that would have astonished earlier generations. Where it fails is not in prediction, but in extrapolation when pushed beyond the domain where its underlying assumptions hold. Science is comfortable with this kind of boundary. Physicists routinely use theories they know are incomplete because those theories capture essential structure while deeper understanding is sought. Quantum electrodynamics, one of the most accurate theories ever devised, is still known to be incomplete. It works because it applies where it is meant to apply. The Big Bang is treated the same way. There is also a sociological dimension. Science is a collaborative enterprise. Shared frameworks allow researchers to communicate, compare results, and build on one another's work. The Big Bang Theory provides a common language for cosmology. Replacing it prematurely, without a clearly superior alternative, would fragment the field and slow progress. This does not mean alternatives are suppressed. On the contrary, many of the most respected physicists actively explore them. Cyclic models, emergent spacetime, quantum cosmology, modified gravity, all are studied seriously. But they are studied as research frontiers, not as replacements for the working model taught at introductory levels. This distinction is often misunderstood outside the scientific community. Popular discourse tends to frame science as a collection of final answers. In reality, it is a hierarchy of approximations. Some are crude but intuitive. Others are precise but narrow. The Big Bang sits at an intermediate level, sophisticated enough to explain vast phenomena, but simple enough to be taught broadly. Another reason the Big Bang persists is that its failures are honest. It does not hide where it breaks. Singularities are not swept under the rug. They are acknowledged openly in the literature. Inflation is debated. Dark components are labeled dark precisely because they are unknown. Tensions in data are published, not concealed. This transparency is not weakness, it is strength. A theory that openly advertises its limits invites improvement. A theory that pretends to completeness stagnates. The Big Bang Theory has endured not because it claims perfection, but because it tolerates challenge. There is also the matter of observational constraint. Cosmology is unique among sciences in that experiments cannot be rerun. We cannot rewind the universe. We cannot vary initial conditions. We observe what exists once. This places limits on how quickly theories can be revised. Models must accommodate sparse, indirect data across enormous scales. In such an environment, conservatism is rational. The Big Bang Theory is deeply constrained by observation. Any alternative must reproduce its successes while resolving its problems. That is a high bar. Many proposed alternatives address one issue while creating others. Until a framework emerges that clearly surpasses the Big Bang in explanatory power, the existing model remains the default. There is also an educational responsibility. Teaching science requires clarity. Introducing unresolved debates too early can obscure basic understanding. Students must first grasp how the universe expands, how light redshifts, how background radiation forms. Only then can they appreciate why these explanations may be incomplete. This staged approach mirrors how science itself develops. Foundations first, refinements later. Importantly, teaching the Big Bang does not mean endorsing a literal beginning. Many educators emphasize that the theory describes early expansion, not creation. Misunderstandings persist, but they are pedagogical challenges, not scientific dogma. At the research level, few cosmologists would claim that the Big Bang represents a final answer to cosmic origins. The real debate is not whether the Big Bang happened, but what it means. Was it a beginning, a transition, a bounce, or an emergent phenomenon? The theory remains silent on this, and that silence is increasingly recognized as significant. In this sense, the Big Bang Theory functions less like a conclusion and more like a boundary condition. It marks the earliest phase of the universe we can describe reliably with current tools. Beyond it lies a region of uncertainty, not forbidden, but unexplored. Science advances by pushing such boundaries outward. The persistence of the Big Bang in education reflects its role as a map, not as territory. Maps are useful even when incomplete. They guide exploration. They reveal structure. They highlight unknown regions by leaving them blank. The mistake is not teaching the Big Bang. The mistake is treating it as the end of the story. When framed properly, the Big Bang becomes a lesson in scientific humility. It shows how far we have come and how far we still have to go. It demonstrates that even our most successful theories are provisional, subject to revision as understanding deepens. What wrong really means in science. When people ask whether a scientific theory is wrong, they are often asking a different question than they realize. In everyday language, wrong implies failure, something to be discarded, corrected, or replaced. In science, the word carries a more nuanced meaning. A theory can be wrong in one sense and profoundly right in another. It can be incomplete, approximate, or limited, while still being extraordinarily useful. Understanding this distinction is essential to understanding the status of the Big Bang Theory. Scientific theories are not statements of ultimate truth. They are models, structured ways of organizing observation and prediction. A model succeeds when it captures essential patterns in nature within a defined domain. Outside that domain, its predictions may fail, not because the model is foolish, but because it was never meant to apply there. This is why older theories are rarely discarded outright. They are absorbed, contextualized, and reinterpreted. Newtonian mechanics did not disappear when relativity was discovered. It became a limiting case accurate at low speeds and weak gravitational fields. Classical thermodynamics did not vanish when statistical mechanics emerged. It gained a deeper explanation. Even Euclidean geometry remains valid in flat spaces, despite the existence of curved spacetime. In each case, The older theory was wrong only in the sense that it was incomplete. The Big Bang occupies this same position. It describes the universe's expansion from a hot, dense state with remarkable accuracy. It accounts for observations across vast scales and times. Where it struggles is at the boundaries at the earliest moments where its assumptions break down. To say the Big Bang is wrong because it cannot describe its own origin is to misunderstand how scientific models function. No theory is required to explain everything. It is required to explain something well. The danger lies not in using incomplete theories, but in forgetting that they are incomplete. This forgetting often occurs when a theory becomes culturally embedded. Over time, its provisional status fades from view, its equations are simplified, its uncertainties are omitted. What remains is a narrative clean, compelling, and deceptively final. The Big Bang has undergone this transformation in public discourse. It is often presented as a definitive answer to the question of existence. In scientific practice, it is nothing of the sort. It is a framework that works astonishingly well within a specific regime and remains silent elsewhere. Recognizing this silence is not an act of skepticism. It is an act of fidelity to science itself. Science advances not by declaring theories wrong, but by asking where they stop working. Those stopping points are not failures, they are opportunities. They mark the edges of knowledge where new ideas are needed. This is why debates about the Big Bang's validity persist. They are not signs of collapse. They are signs of vitality. A field that questions its foundations is a field that is alive. There is also an emotional component to the word wrong. People often feel that if a theory is incomplete, it cannot be trusted. In science, trust is contextual. A theory is trusted where it is tested. It is treated cautiously where it is extrapolated. This layered trust allows progress without paralysis. The Big Bang is trusted as a description of early cosmic expansion. It is treated cautiously as an account of absolute origin. Confusion arises when these roles are conflated. Asking whether the Big Bang is wrong, then, is like asking whether a map is wrong because it does not show what lies beyond its edges. The map may be accurate where it applies. Its blank regions are not errors. They are admissions of ignorance. Science values such admissions. They guide inquiry. They prevent overreach. They keep explanation honest. There is also a deeper philosophical lesson here. Human understanding is inherently limited. We build models that capture aspects of reality, not reality itself. Each model reflects the tools, concepts, and questions of its time. As those evolve, so do the models. The Big Bang theory emerged from a specific historical context, a convergence of relativity, astronomy, and observational technology. It solved problems that earlier frameworks could not. It will likely be reframed or extended as new tools emerge. This does not diminish its achievement. It places it within an ongoing process. In this light, calling the Big Bang wrong is less informative than asking how it will change. Will it be embedded in a quantum theory of gravity? Will it be reinterpreted as a phase transition? Will it become one chapter in a longer cosmic story? These are open questions, not failures. Science is comfortable with open questions. Certainty is not its goal. Understanding is. The persistence of uncertainty at the universe's origin is not a weakness of cosmology. It is a reflection of the scale and complexity of the problem. We are attempting to describe conditions far beyond any direct experiment, using theories known to be incomplete. That we can say anything at all is remarkable. The Big Bang, then, is not a wrong answer to the wrong question. It is a partial answer to a very hard question. Treating it as final does it a disservice. Treating it as provisional honors its role. What replaces the Big Bang if it fails? When a scientific theory reaches its limits, it is rarely erased. More often, it is absorbed into something larger. The question, then, is not what happens if the Big Bang is proven wrong in some absolute sense, but what framework could take its place? What deeper picture might explain both its successes and its failures? History offers guidance. Newton's laws were not discarded when relativity emerged. They were reinterpreted. They became approximations that apply under certain conditions. The same fate likely awaits the Big Bang. If it is replaced, it will not vanish. It will become a special case within a broader theory of cosmic evolution. The most likely candidates for such a theory arise where current understanding breaks down, at the intersection of gravity and quantum mechanics. Any replacement for the Big Bang must explain expansion, structure formation, background radiation, and element abundances, while also resolving singularities, fine-tuning, and horizon problems. This is a demanding requirement. It narrows the field significantly. One possibility is a fully developed theory of quantum gravity. Such a theory would describe space-time itself as a quantum object, capable of fluctuating, transforming, and emerging. In this framework, the universe's earliest phase might not involve classical space or time at all. What we interpret as the Big Bang would be the moment when space-time condensed into a form describable by classical geometry. In this scenario, the Big Bang is not replaced so much as reframed. It becomes the boundary between quantum reality and classical reality. Expansion begins not because something exploded, but because space-time acquired new degrees of freedom. The universe started only in the sense that familiar physics began to apply. Another possibility lies in emergent cosmology. In these models, space and time are not fundamental ingredients of reality. They arise from deeper structures, networks of information, entanglement, or statistical relationships. The universe is not born, it crystallizes. What we observe as expansion may reflect changes in underlying connectivity rather than physical stretching of space. Such ideas are radical, but they address a recurring problem in cosmology: our reliance on concepts that may not apply at the deepest level. Distance, duration, and causality may be emergent features, not fundamental ones. If so, asking what happened before the Big Bang may be as misguided as asking what lies beneath the lowest floor of a building. There are also hybrid approaches. Some theories retain expansion and early heat while replacing singular beginnings with smooth transitions. Bounce models fall into this category. They predict a contracting universe that reaches a minimum size before expanding again. Quantum effects prevent collapse into infinity, preserving continuity. In bounce models, the Big Bang becomes a turning point. The universe's history extends beyond it, but that history is partially hidden. Information from before the bounce may survive only in subtle ways, encoded in large-scale patterns or statistical distributions. Detecting such signatures is difficult, but not impossible. Multiverse frameworks offer another path. In these models, the Big Bang is one event among many, each associated with a different region of a larger structure. The universe we observe is local, not total. Its apparent beginning reflects the limits of our observational horizon rather than the limits of existence itself. Multiverse ideas are controversial because they challenge testability, but they emerge naturally from certain inflationary and quantum theories. They attempt to explain fine-tuning by embedding our universe in a broader ensemble. Whether this approach clarifies or complicates cosmology remains an open question. What unites all these possibilities is a shift in emphasis. Instead of asking how everything began, they ask how structure arises, how laws emerge, and how transitions occur. The focus moves from creation to process. This shift reflects a deeper maturation of cosmology. Early science sought origins. Modern science seeks mechanisms. As our tools improve, explanations become less narrative and more structural. The universe is understood not as a story with a beginning and end, but as a system governed by evolving rules. Replacing the Big Bang, if it happens, will not be a dramatic overthrow. It will be a quiet reorganization of understanding. Textbooks will change gradually. Terminology will evolve. The Big Bang will remain, but its role will be redefined. It is also possible that no single replacement will emerge. Cosmology may remain pluralistic, with multiple models describing different aspects of reality. This is not failure, it is specialization. Just as physics uses different theories for different scales, cosmology may use different frameworks for different epochs. In this future, the Big Bang might describe early expansion, while quantum cosmology describes pre-expansion states, and emergent theories describe the origin of space-time itself. Each theory would be incomplete alone, but coherent together. This layered approach aligns with how science has always progressed. No theory explains everything. Each explains something well. Together, they form a mosaic. The possibility that the Big Bang could be replaced or reframed is not a threat to science. It is a sign that science is working. It reflects a willingness to revise foundational assumptions in light of new insight. The universe does not owe us a simple origin story. It owes us consistency. Our task is to build models that respect what we observe without pretending to know what lies beyond the edge of evidence. Why this question matters more than you think. At first glance, the question of whether the Big Bang theory is right or wrong may seem remote, an abstract debate confined to physicists, equations, and distant galaxies. It does not change how the sun rises or how gravity holds us to the earth. Daily life continues regardless of how the universe began. And yet, beneath the surface, this question reaches far beyond cosmology. It touches how humans understand knowledge, meaning, and their place in reality. Origin stories matter. Every culture, across history, has told stories about beginnings. These stories do more than explain where things came from. They shape identity. They establish context. They influence what people believe is possible, meaningful, or inevitable. Modern cosmology has inherited this role, not intentionally, but by necessity. In a scientific age, the story of the universe's origin becomes a story about us. The Big Bang, presented as a definitive beginning, offers a sense of closure. It places existence within a timeline with a clear start. For some, this is comforting. For others, it is unsettling. But in either case, it frames reality as something that happened once, long ago, and has been unfolding ever since. If that framing changes, if the universe has no singular beginning, or if the Big Bang represents a transition rather than creation, then the narrative changes as well. Existence becomes less like a story with a first chapter and more like an ongoing process without a clear starting point. This shift has psychological consequences. Humans are drawn to final answers. We seek certainty, even when uncertainty is more honest. A universe with a beginning feels explainable. A universe without one feels open-ended, incomplete, and resistant to closure. Yet science repeatedly teaches that reality does not conform to narrative convenience. It unfolds according to structure, not story. The debate over the Big Bang reveals something important about how knowledge works. Scientific understanding is provisional. It evolves. What feels settled today may become contextual tomorrow. This is not a weakness of science, but its defining strength. It is how understanding deepens without stagnation. Accepting this provisional nature requires humility. It requires comfort with not knowing, and it requires distinguishing between usefulness and finality. The Big Bang is useful. It organizes observation. It guides research, but usefulness should not be mistaken for ultimate truth. This distinction matters beyond physics. In many areas of life, People mistake models for reality. Economic systems, social frameworks, and political ideologies often persist not because they are perfect, but because they work well enough. Problems arise when these systems are treated as final rather than flexible. Cosmology offers a parallel lesson. Even the most successful models must remain open to revision. The question of cosmic origins also influences how humans view meaning. If the universe began suddenly and will end definitively, existence may feel fragile, temporary, accidental. If the universe is eternal or cyclic, existence may feel more continuous, less precarious. These interpretations do not determine meaning, but they shape the emotional landscape in which meaning is sought. Importantly, science itself does not assign purpose. It describes structure. But the stories built around scientific ideas inevitably carry philosophical weight. When the Big Bang is framed as the moment everything came from nothing, it invites metaphysical interpretations that science itself does not require. When it is framed as a transition, those interpretations shift. This is why precision in language matters. Saying the universe began with the Big Bang is different from saying the observable universe expanded from a hot, dense state. The first suggests creation, the second suggests evolution. The difference shapes how people think about existence, causality, and the limits of explanation. The Big Bang debate also highlights the boundary between science and belief. Science asks how. Belief often asks why. When scientific theories are stretched to answer questions they are not designed to answer, confusion follows. Recognizing the limits of scientific explanation protects both science and philosophy from overreach. There is also a cultural dimension. Science, especially cosmology, carries authority. When it speaks about origins, its words are taken seriously. This authority must be handled carefully. Overstating certainty undermines trust when revisions occur. Acknowledging uncertainty builds resilience, allowing understanding to evolve without disillusionment. For future generations, how we frame these ideas will matter. Teaching the Big Bang as an unquestionable fact risks turning science into doctrine. Teaching it as a powerful but incomplete model invites curiosity. It encourages questioning. It aligns education with the actual practice of science. The question, is the Big Bang theory actually wrong, is valuable not because it demands a yes or no answer, but because it invites deeper thinking. It asks us to consider how knowledge is built, how models function, and how understanding grows. It reminds us that certainty is not the same as truth. In this sense, the debate is not about replacing one story with another. It is about resisting the temptation to close inquiry prematurely. The universe has surprised us before. There is no reason to assume it will stop. As we approach the final chapter, the question shifts once more. After all the evidence, all the models, all the alternatives, what can we honestly say? Not as a definitive conclusion, but as a careful summary of where understanding stands today. The final answer. After all the equations, all the observations, all the debates and revisions, we return to the question that began this journey. Is the Big Bang theory actually wrong? The most honest answer science can give is not a simple yes or no. The Big Bang theory is not wrong in the way a disproven idea is wrong. It is not a mistake to be erased or a failure to be corrected. It is something more subtle and more revealing. It is a theory that works extraordinarily well within the domain it was designed to describe, and then grows quiet when asked to speak beyond that domain. It explains expansion. It explains cooling. It explains structure. It does not explain absolute origin. This distinction matters. The Big Bang describes how the universe evolved from an early hot, dense state into the cosmos we observe today. It does not, and was never mathematically equipped to explain why that state existed, whether it was the first state or whether first even has meaning at the deepest level of reality. When people say the Big Bang is wrong, what they often mean is that it feels incomplete, and they are right, but incompleteness is not failure. It is the natural condition of scientific understanding at the frontiers of knowledge. Every major theory in history has shared this fate. Each explained more than what came before it and less than what came after it. Each was once treated as final. None were. The Big Bang Theory now occupies this familiar position. It is a powerful framework that has reached the edge of what it can say. Beyond that edge lie questions that demand new concepts: quantum gravity, emergent space-time, deeper laws not yet known. What fails at the beginning of the universe is not reality. What fails is our description of it. The singularity does not tell us that everything began from nothing. It tells us that our equations cannot follow the universe all the way back. Inflation does not close the story, it postpones it. Dark matter and dark energy do not explain mystery away, they name it. This is not cause for disappointment, it is cause for perspective. Science is not a collection of final answers. It is a process of refining questions. The Big Bang remains one of the most successful scientific achievements ever developed, not because it explains everything, but because it explains enough to reveal where explanation breaks down. That breakdown is not a dead end, it is an opening. It suggests that the universe may not have begun the way stories require. It suggests that time may not be fundamental. It suggests that creation may be the wrong metaphor altogether. The cosmos may be older, deeper, and more continuous than our current language allows. So is the Big Bang Theory wrong? No, if we mean wrong as in useless or false. Yes, if we mean wrong as in incomplete, provisional, and awaiting a deeper framework. And that second sense of wrong is not a flaw. It is the engine of progress. The most important realization may be this: the universe does not owe us a beginning that fits our intuitions. It does not owe us a moment of origin that can be neatly placed at the start of a timeline. It only offers patterns and invites us to understand them as far as we can. The Big Bang marks the earliest chapter we can currently read with confidence. What lies before it remains unread, not because it is forbidden, but because we have not yet learned the language. And that is where science remains most alive. Not at the answers we think we have, but at the questions that refuse to disappear.